Hello everyone. So welcome to the CTQ5. So we'll discuss what maximum things possible about this circuit. The actual question was to plot the or find the output swing for this varying input between 0 to VDD. So actually this is very important structure. Later in coming CTQ, I think CTQ 8 or CTQ 9, I have taken or compared few such structures where you will see some more detail about some other structures like this. The simple concept of the circuit is that I want to implement an inverter. So this is one inverter structure having different kinds of load there. So this thing I learned about any such circuits in a book called Alan Hallberg. You can see there why this structure is generally there are many topologies of the inverters, out of which this is one. Okay, so this is one the inverter I can say inverter with diode connected PMOS load. Diode connected PMOS load. So we can see there are many different structures of for the inverter you can see later, but in general for the small signal purpose or for the gain purpose we use it as the common source amplifier also it is used as common source amplifier. What we can see here in this particular problem, I will analyze this circuit based on the input which is varying from 0 to VDD. So more like we are interested in DC analysis. But for the small input signal for particular DC bias for the particular common mode, this is nothing but a well working or common source amplifier. Okay, it will not give proper gain. This is not the concern of this video, but point is that a particular inverter for which we have to sweep our input from 0 to VDD and we have to see the output. So these are the kind of questions that in the interview can be asked. There are many other topologies are there. Instead of M2 I can use a ideal current source, I can use a resistor, I can use some PMOS with the external bias at its gate. So there are possible topologies which you will see in the CTQ9. For a time being, I will discuss what output we will look for this variation of the input and what other possible variations of like different plots that I have taken means GM plot and ID plot. Okay, so for this not only will expect or not only we will see the output voltage swing, we will see the GM also. GM means usually we are applying here the input at the gate of first transistor. So the drain current that is flowing across this structure is nothing but a drain current of M1 also. So we can see the whatever the GM plot or nothing but a current versus voltage plot differentiation you can see is a kind of GM plot. Okay, so we will see one by one. So what is happening here actually? So in this structure you can see when your Vin is let I just draw here VDD, how I will approach it. This is my Vin, it is out. Okay, so this node is connected to drain, so it is diode connected device, and this is M2 M1. So what I will take some test cases or some cases where you can understand. Suppose my input is less than VTH of M1, that I call VTH of 1, or I will say it as a VTH of N. Only two transistors are there, M and N. So if it is less than this, what it says that your M1 is off. If M1 is off, then what you can see, there should not be any current. Ideally, there should not be current. If M1 is cut off, then ID1 equal to 0. So hence it is equal to ID2. So ID equal to 0. So what we are expecting for particular input less than VTH, our current should be 0. That is the ideal spec. Practically you will see that M1 in the M1 the current can flow for the voltage near the VTH. that we call the subthreshold conduction also. We'll see it later. So this is happening. Now what I can see, the two things that I can observe in the circuit, even before going to this input less than VTH, I can see one thing. So even putting any condition on the input, I can go for one thing. This is my input, this is fed back to here. So what I can see here, if I talk about this current, the current of transistor 1, what it is following, actually it is nothing but a function of its own VGS, that I call VGS1, or I will say it is a function of V in itself. It's true. So from here I can say this M1 is what? From here we can say M1 is voltage controlled current source. Actually we are applying the input or the gate terminal, because there are two terminals for any particular transistor, gate and source. If their two terminals are fixed already, or then I can say I am forcing particular current in this device, because we know that VDS has weak dependence for the current. Okay, so this input is directly appearing as a VGS, so I can say that this ID1 current that is generating across the M1 is directly function of the input. Okay, so my input is a current controlled voltage source. What about this device? What I can say, if any one of you know, for any diode connected device, the VGS, for the PMOS here, I will say the magnitude of the VGS is nothing but the current flowing across it, that I call it ID2, divided by KWIL plus VTH of this particular device. So this equation I have written from the saturation condition, from the saturation region equation of current, saturation region equation of current. Okay, so anyway, what we can see, there is a particular current flowing across this M2 also, that I call ID2, that they are in series. So I can say always ID1 is equal to ID2. But what I am observing here, the first device, that is a M1, is controlled by the input voltage. The current we are getting out of it with a particular relation, whether where the device is operating, depending on that, I am getting some current, and that current is flowing through the M2, so that we are getting the VGS across it. This is the relationship that I am getting for the saturation region. We will have some other relationship with the other dependence of the current, but point is that this M2 has no current generation by its own, because its drain is source is fixed at VDD. Its gate, or I call the drain here, it is kind of dependent on the current what is flowing through the M1. Okay, so if the current will increase, that we can see that VGS of our device, you can see from the N relation, the VGS of our device, or I will say VDS of M2, is proportional to whatever the proportionality of the relation or the current ID2. So if I1 increases, ID2 will increase, because they are in series, so VGS will increase. So what is going to happen from this relation, we can see, as my ID2 is increasing, because my VN is increasing, so what will happen in the consequence of this, VGS2's magnitude will increase. So it means it will also increase. It means VDD minus VGS2 magnitude, what will happen with this thing? It will decrease. And who is this? This is nothing but your output. This is your output. So this should be the way of analysis. When we explain in front of the interviewer, you should approach any simple question like that, so that they can have the feel that you are understanding the things in great detail. This can be like a proper way of explanation of the question. Directly we can see the question is like a simple inverter. If you are swinging the input from 0 to VDD, your output will be going from VDD somewhere to near to 0. But we will see the exact technicalities near that. So one more thing, this is the one observation that I can see from here. Okay, so actually the VGS generated across the M2 transistor is nothing but dependent on the current, and this current is generated by the M1, which is nothing but controlled by its input voltage that we are swinging from 0 to VDD. Okay, so from here we have observed that the output node is nothing but a VDD minus VG of the second transistor, and VGS is increasing as current is increasing. So overall VDD minus VGS2 quantity is going down, means output is going down slowly. That way we are getting the inverted relation. On the one side we are increasing the input. Okay, on the one side what is happening, we are increasing the Vin, and we are getting what, we are getting decrement in output. So this, because of this particular nature, I will call it inverter. Okay, this is the only nature the inverter follows. If input is increasing, output will decrease. If output is decreasing, if input is decreasing, on the other hand, the output will increase. So this is nothing but a phenomena of inverter. So this is the first takeaway that I can get from here. First, one device is the current controlled voltage control current source, and second device is the current controlled voltage source. So I can say it is a current controlled voltage source. Okay, so now what extra we can get out of it? Now I will see the nature of M1, how it is operating, and how it is setting the output voltage, and how the output voltage actually is coming. We will see it. Okay, so M2 is free, means whatever current it will get, I will set my voltage. The M2 is free. The main job that is my current is doing here. So M2 is sitting with the relax that what amount of current I will get, I will set my VGS according to that, and so that this voltage, I call it output voltage, will be set. Okay, so if I go through the characteristics of M1, that what I will see, ID, this is my VGS of M1 that I call VN, VN. So what we'll see, up to somewhere near this threshold N, we are somewhere 0. So I'll change the color. Okay, so till this point we are nearly 0. Because of subthreshold conduction there will be something. So what is happening here? So because we are, the current is 0 nearly, till this point my ID is 0 nearly, or ID1 and ID2 both are 0. So what is the nature of M2 at that time? I have to see this also. So M1, this is fine. Now I have to see what is my V out at this instant before this VTH. So we will see that because the M1 is not taking any current till this point, as ID1 is 0, hence ID2 is 0. So M1 is not taking any current. So what should actually happen with this output? So from here, the M2, this is my VDD, and this is the condition that it is taking 0 current across it. What is the possibility that this node should be? Actually, this node should be what? VDD minus VTH of P, that is a magnitude. Ideally, this node should be this, because when this node will reach this or above this, then what will happen? Actually, my VSG will be nearly equal to VTHP. So when my VSG is less than VTHP magnitude, we will say that my MP is also off. M2 or MP is also off. Then only this condition can be satisfied, because both the transistors are in series. So the condition of having 0 current can only be satisfied when our VSG is less than VTHP. So it means what we can see, the drain voltage of this M2 or the output should be less than VTHP. Means less than VDD minus VTHP, or sorry, greater than VDD minus VTHP, so that the VSG can be less than VTHP. Okay, so now point comes, what is the exact value of output? That we have to see. So what I am seeing here, that according to the PMOS condition, according to the PMOS, this it should be anyway greater than the VDD minus VTP. So I will say this will be nothing but VDD minus VTHP ideally. But if you will go practically, this is my ideal output. Okay, but what you will see when my output is just VDD minus VTHP, or VGS is, what is this for the PMOS? My VSG is, or I can say VGS magnitude for the PMOS is equal to, exact equal to VTHP. So is transistor complete off at this particular value? No, transistor has, because transistor has what, VDS is also there, because transistor has VDS also, which is nearly equal to same VTHP, or exactly equal to VTHP I should say, because we are on output equal to this only. Okay, so it means across the transistor we have drain to source voltage, and our VGS is just at the strong inverse region, that is equal to VTH. So there is a flow of subthreshold current. So there is a flow of subthreshold current. So this point I will explain with some device physics level. Okay, so what is happening here? Actually, this is a case of PMOS. No problem. I'll take any case. Let this is my NMOS. So here my oxide is there. This is my VG. This is my V source. This is my, this is the body somewhere on. Okay, like this BB. For time being I am considering this equal to Vs. Okay, and the lowermost potential, that is anything can be, if it's NMOS. Okay, so what I want to analyze, my point is not here to talk about the body effect, it can be anything. Okay, so actually lowest potential of the system, because for NMOS. Okay, this is my NMOS structure. So what I want to see from here, as my VGS is nearly VTH, so what we are seeing at that time, if it is a, just consider if it is a like a PMOS, I have taken the NMOS. If instead of that there is a PMOS, VDD is already there. Suppose this is a 0.5 and it is nearly, I will say, this is my 0.2, and they are equal, means source and means, or what I say, drain and gate are equal, that I will say this is also 0.5 volt. Okay, 0.5 volt, 0.5 volt, 0.2 volt, and let this is my VTH also, VTH of N also. Okay, so what I'll see, the channel is just formed here. Okay, the electrons are available in the channel is just formed, and we have difference also. So what we can see here, the channel is developed already, because we have the VGS equal to VTH, VGS equal to VTH, or what I'll say means that source I have connected to the 0.2. I think this is not a good thing. I should say this is my 0 volt. I just random example. So this is my 0 volt. Okay, so I have what, VGS is what, VGS is 0.5 volt equal to VTHN. So we cannot say, ideally the current can be 0 and near this point, and current can be 0. This is my ideal case, but practically the current is not 0. This is called practical, because VDS is already there, so force is already existing from this direction to this direction. Drain to source, force is already there, electric field is already there, electrons are available, just the channel is formed. It is not that strong inversion, but you are at the edge of this channel formation, so this force is available, so some current will start flowing. So here the ID is not 0, this is called a subthreshold current. Subthreshold current. Even not exactly that, even this current flows for VGS less than VTHN of the few magnitude order. This is like, this is my curve. What I can say, exactly my VTH is here, then before VTH the current can flow, because of these channel carriers are already there. It is not a strong inversion, but carriers are there. So in this region also the current can flow. So this is particular called subthreshold conduction. Okay, in this relation, in this particular region, the dependence of ID on our VGS is nothing but an exponential relation. Okay, so it is important. In the subthreshold region, in the subthreshold conduction region, the current has a dependence or exponential dependence on the input. So the few microvolt change in the input can cause huge difference in the current in this particular region. So there is a current, of course there is a non-zero current. This is the concept of non-zero. So why I picked this concept here, I will now again go back to the circuit. Okay, so what is happening here, this is my PMOS. For the PMOS, when I assume that my output is exactly VDD minus VTHP, in that region, due to the subthreshold, this capacitors, which are drain capacitors, I need not to go into the depth, but there are some capacitors which are drain capacitor, I call CDS for both the transistors. Okay, it will remain charging because this current is not exactly zero. There is some flow of current still there. Okay, so the drain caps will have the extra means it will store charge, it will remain storing the charge. Or I can say this node is not going to stop here only, it will approach somewhere near VDD, that I will call VTHP. It will go above this. Okay, that will be the delta V amount. So this delta V, if it can exactly be the VTHP, then it will be near to the VDD. But I will say it is not going to near to the VDD, but even it is not going to stop at the VDD minus VTP also, because of the subthreshold conduction. So because of subthreshold conduction near to VDD. But the problem is, the point is, the input is very less now. So it can reach the VDD, but at this point is not our consideration. So in general, it is not the part of our consideration, because it is of no use. The output can reach there, but it is of no use. So this was a point I was trying to make here. Rest question we will solve easily. Okay, so it can happen, this output can really reach the VDD for this particular amount, but what we will see now. Okay, now my input is going above, now Vin is going above the VTHN. Okay, so the current will flow, no problem, current will flow, start flowing. So this is my VTN. So what is the reason of this your M1 here? So reason of M1, so the reason of M1 will be nothing but saturation. And what is the reason of your M2? That is also saturation, because it is diode connected device, so always forced into saturation. So why M1 the question can be asked also in any NMOS. If any NMOS, there is a PMOS on top of that, so no problem. In general, when we are applying the gate voltage to the NMOS and the gate voltage is just reaching out of or reaching above the VTH, then what we can see, this NMOS always starts in VDD, because start in means saturation region. Okay, this thing we can see. So okay, so if there is any means, I am not just forcing it, if there is some resistor, which is not the point here, so this is the VDD. Okay, so as I am forcing this input, if my VDD, this output is near VDD, I should say this is my output, V out is near VDD when my input is less than VTHN. So as my input is just crossing the VTHN, and my input is crossing by VDS is what? VDS for this transistor is nearly VDD. Okay, so what I can see here, this overdrive voltage is what? VGS minus VTH, and it is nearly 0, because we are just above the VTHN. Okay, so just above the VTHN, what will happen? Your overdrive is nearly 0 and your VDS is much greater VD is much greater than the V overdrive, or I call it as a VD set. So there is a strong saturation region, strongly in saturation region. So NMOS always starts in the saturation region. So what we see here, the ID, this is my Vin, it is starting in saturation region. At the same time, the output is also going low, that we have seen already, because the expression of output is what? Vout is VDD minus VGS of P. Okay, so this output is also going low. As the current is increasing, the output is going low. Okay, so what you see at particular point, when VDS of N is equal to VGS of N minus VTH of N. What I should say, this is I will call Vin minus VTHN, this I will say Vout. So what do you see, when Vin is equal to Vout plus VTHN, at that particular amount my transistor M1 will enter into linear region, So exactly what you see, the current, the dependence on the input is not exactly the quadratic. Here in this quadratic, this is the point where this input is equal to Vout plus VTH of N. After this, there is a linear increment. So the both nature are different. This is not a discontinuity, but yeah, you can see the nature are different. So here the current is a quadratic. I will say here my current is quadratic. So this is my quadratic, and here my current is linear function of input. So this thing can be seen, but it is not that visible. I have just differentiated, but it is not that visible. You can see directly the running plot. If you will simulate also, you will see the running plot. So what happens when the VGS is continuously increasing? Will the current will remain increasing, or it will stop somewhere? Yes, it will stop. So what you can see, if I go for the current plot, so as my Vin is increasing, so now my Vin is much greater than my VTH, much greater than in the sense means amount is now much above this VTH. And what you can see, we can see current is still increasing. What saturation of current will come? Saturation of current. Because what the problem? Actually, what I am seeing that VDS is reducing. VDS of M1 is reducing continuously. That you can see here. This Vin is increasing continuously, and this is nothing but the drain of NMOS is nothing but output, and this is decreasing continuously. So what I am seeing, this VDS is going down continuously. Okay, so actually what we can see, the force which is forcing the current for NMOS particularly, this the electric field, which is forcing this current or the electrons which are inside this channel. So the electrons, the flow of the electrons, the current electric field, from this we can see this, as VDS is reducing, this force is also reducing. So whether you are going with a stronger region, the device is strongly on. As Vin or VGS is nearly reaching the VDD, device is strongly on. Device is much strongly on. But VDS is limited, so velocity saturation. So the reason of velocity saturation is not only that the VDS is going low, even the VDS is high, even my VDS is enough, then also what you will see, if your carriers in the channel are increasing much, if the carrier channels are much, then also the velocity saturation can occur. because the mobility limited by number of carriers also. So actually what we are doing here on the device scale, what we are doing here for the NMOS, we are continuously pumping or continuously forcing our gate to accumulate more and more electrons. This gate is continuously forcing more and more electrons, so the channel has lot more density. The channel is much dense. It is dense. Okay. So whatever this gate to source, sorry, drain to source, or whatever. So what are the drain to source voltage here? This electric field is much high. This electric field is very high because we are forcing, or we are applying more and more VGS, or V the input voltage, because we are applying input voltage much higher. Input voltage is much higher. So even we are applying a lot of voltage on the gate, we cannot expect the current will always be increasing. This is due to the velocity saturation. Okay, too many carriers cannot propagate so easily. It can be understood like this is a just example. There is a room, there are few peoples or few children are there. They can easily walk and play. Whatever they want to do, they can do. Easily walk and play. But what you say, the same room, there are many children. Okay, there are too many children are there. So the speed of walking speed, or I should say walking and playing, will be hindered because of the too many carriers in particular region cannot propagate with the same speed. So we are forcing from this side that they should run, but there is enough crowd, they cannot run. You can see this thing also in the metro stations. You can also see on the metro station, in any crowd place, any crowd, you can see whatever we are saying that move fast, but in front there are a lot of the carriers, a lot of the people are there, they cannot move fast. But here, if this force is there, they can move fast. So same thing is happening here. This is nothing but V in we are applying. The force we are applying, and here the carriers are less, so they can move or they can walk faster. So here we can say the current is increasing. Current is increasing as we are increasing the input. But here what you will see, current will saturate. It has not enough space for the carriers to walk faster. Okay. So ideally what should I see here? This is the limitation imposed by the NMOS. So actually we are looking for the limitations of NMOS only, because the PMOS is nothing but it is just creating the voltage across it, that is a VGS, because depending on the current. So for the response of current, accordingly it will generate the VGS, and hence my output will be generated. Okay. So what I say, if I should see this current, nature of the current that I should see. So as we have seen from the point of velocity saturation, whatever the amount we are increasing, we cannot increase it in too much, because we can, why I have given the condition that you can go to the VDD, because we will see one more concept that I should discuss here. If there are any MOS, this is suppose a 1.8 volt device, then what is expected? VGS greater than 1.8 is not recommended. You can go somehow, it means they are something like that. If you are applying VGS of 5 volt for the 1.8 volt device, oxide will break. Oxide breakdown will happen. So any particular device is not designed such that you can apply the 5 VDD or what I say 4 VDD. You cannot apply like this. That's why we are going like this. Okay. So this is the limitation for the device. So we are going to the input of VDD only. The device can break. The oxide that I used here, this is my oxide, it will break. Yeah. Okay. So okay, what I am seeing, the current is limited. Now now the output is reducing continuously. This output somewhere will reach the VTH of n. Okay, so what will happen at that point? Okay, so I think there is no problem in that because my VGS is enough, so it is not going to create any problem. So it can go lower, lower, lower. Now it is reaching near VDD, sorry, near ground, near ground. If my output is reaching near ground, what is happening here? VDS of n is reaching to 0. So what will happen at that time? My VGS is nearly VDD, my VGS is nearly VDD, and VDS, for the NMOS I am talking, for VDS is 0. So what is the overdrive voltage? That is VGS minus VTH. So VDD minus VTH of n. Let I call this is 1.8, this is the 0.5. Then what is my V overdrive? It is nothing but 1.3 volt. Okay, so it is too much greater than this my VDS, which is nearly 0. So what we can see here, this is the strong linear region, strong linear, or I would say triode region, strong triode region. Okay, so what is happening here? Strong triode region. But in the triode region, my NMOS can behave as a, okay, my NMOS can be like a resistor. So what will happen? Okay, so what we will see, this NMOS is reaching, NMOS is in triode. Okay, so around this condition, my NMOS is in. So we know the relation of the triode is that what will be the R on. My NMOS can be replaced as a resistor from drain to source, which is ground. This is my R on. Okay, so when my NMOS is linear, it can be replaced as a resistor. But as we are seeing, the VGS is going lower, lower, lower. So we can see, oh, sorry, VDS is going lower. So it is entering into much deeper. So the R on can be found like, what is the R on? R on is 1 upon mu n CUX WIL VGS minus VTH. So from this relation, yeah, this relation is nothing but I think everyone knows. In the linear region, what is happening? Mu n CUX WIL, that is VGS minus VTH, VDS minus VDS square by 2. Okay, so I am assuming that our VDS is much lower. If VDS is much lesser than VGS minus VTH, because we are knowing that at this time we are somewhere here at 1.8, this is nothing but 0.5, so this amount is nearly 1.3 volt. So we can say VDS, which is nearly 0, is much less than 1.3 volt. Okay, so what we can assume here, this equation can be approximated. I am just calculating the R on. I would like here the R on calculation. Okay, so ID can be approximated like mu n CUX WIL VDS. Okay, this equation, this particular term can be approximated to 0. So what is the R on? It is nothing but differentiation of this current. This is the 1 upon R on. It is coming as mu on CUX WIL VGS minus VTH. Okay, so that thing I have written. The R on is nothing but inverted of our equation. Okay, so this is the R on. So what we can see, as I am reaching near to this VDD, so VGS minus VT is a constant term, so it is a constant resistor. So after that, a constant current will flow across it. So who will support this constant current? So from this, what we can understand, our output will not reach 0, because yeah, it can, this is my output. So what we are seeing here, because my this V in, which is a VGS, is VDD, it is too high and current is saturated. So what you will say, this is my some amount, let's say it is near the ground, I will say 100 millivolt. Then this is my constant resistor. This N mod is a constant current term, model it is R1. What you see, a constant current will flow. So one more thing is, why it is not going to 0? Can this V out go 0? If V out will go 0, what you will see is ID should equal to 0. But we are seeing that in this region current is not 0, it is nothing but saturated. So I would say like it is nearly saturation. So here it is saturated. So current is not 0. So I will call say for particular, like I will say 50 microamps, it is saturated. So anyway, because this is a series current with both NMOS and PMOS are series, so this saturated current need to be supported by NMOS. What is C? The saturated current need to be supported by NMOS also, because they are in series. So what you will see, let the I have to see, if I say that this is my 50 micro is a saturated current, then I will see what, and what is my V out, and from here R1 we can see. So this is a nearly constant. R1 I can get from the other constant term at the VDD, and so V out will be some constant value. So what is the V out exactly? If I am just giving a rough numbers, if my ID is 50 microamps, just I am taking rough numbers, and my R1 is suppose my 100 ohms, what you will see, the V out is ID and R1. What I can say, 50 microamp into 100 ohms, so it is my 5 millivolt. Okay, so it is not going to 0. Just I have taken the random numbers, it can be anything. So now I will show actually what we have seen, GM plot. So in GM plot also, what you can see, or GM plot I can see transconductance block, the current is like this. Okay, so this is my input, this is my not output, it is my current. What you see, this current is increasing and saturating somewhere here. So this slope of del ID by del V in, which we call nothing but transconductance, is increasing here up to the ID 0, VTHN, up to the 0 ID is 0, and after that somewhere in middle the slope is maximum. Okay, somewhere in the middle the slope is maximum, so GM will take some maximum value in this region, and after this current is saturating, so it will saturate. Okay, so overall I can say somehow this kind of GM plot you can see, because of velocity saturation, you will see the GM is also increasing like this, and it is increasing in some function, and after that it is reducing and constant. So this is somehow, this is nearly midpoint, mid. Okay, so till this VTHN, whereas current is 0, so GM is also 0, and it is increasing and it is getting maximum here. Okay, and after that it is reducing, because of this reduction is in velocity saturation region, where my current is constant, velocity saturation, due to this, because what we are seeing, the input is increasing and current is nearly constant. So this curve, the slope of my del ID by slope value del ID by del V in will decrease. So this is that. So now the conclusion, what we will see, or the output plot. So I can say it is somewhere higher going like this, and after that this, and it is nearly some here value. This is my V in equal to VDD. This is my 0. This is something VTHN. Okay, so this point will try to reach VDD, but I will say it is VDD minus VTHP plus some del V. So it will try to reach near VDD. Okay, this is V out, this is my input, and it is not exactly 0. It is also, it may be a few millivolts, it can be few millivolts, but it is a non-zero value. Okay, because it has to support the saturation region, a saturation current, the saturated current, which is nearly, I can say, somewhere here it is saturated. Okay, so I think maximum things are covered here. So if you directly ask me the swing, then I can say swing in general, you can say that it will reach VDD minus VTHP. Maximum value is my maximum, and it can reach 0 as a minimum. Okay, so between these you can see swing. This is in general, you can say, but more insight you can see from this video discussion. In general can be said. Okay, so I've also taken these plots, and you can see the value just for this shown. Okay, what you will see here, you will see this is my output plot, this is my V out plot. It is for 1.8 device. When when my input is nearly 0, this output is somewhere, this value is 1.67 if it is visible properly. So it is reaching nearly 1.67. It means it is only 130 millivolt away from my VDD. Okay, so it is trying to reach the VDD 130 millivolt away from the VDD. Okay, and a lower value I am seeing here, 211 millivolt, 211.4, that I will say 211.4 millivolt. So I should, it is a something like that. It is not exactly 0, that we can see from the simulation. And around the 480 is a VTH, this is a VTH point, and after that current is increasing, and it is saturating somewhere. So somewhere here it is nearly means 30.4 some microampere. It is saturating somewhere here. And what we have seen, this region is the maximum slope region. So here you can see, okay, so you will see somewhere near, this is like 0.9 volt. So my scale is going to 1.8 volt maximum. So I have seen, I already told this thing, it is occurring around the midpoint, which is 0.9 millivolt. Okay, so from this plot you can see the maximum things are clear. So for this particular graph, here is the maximum plot that I am getting. So the GM value for this graph I am getting 46.8 microsiemens. Okay, so it is occurring near the midpoint. So what we can see in general, what we will see that for any particular transistor or the amplifier, if we are designing, we should first sweep the input, and we can see that GM is occurring somewhere maximum at the midpoint of the input. So usually this we call the biasing of this transistor. So this is usually bias point. 0.9 is a bias point, and around this bias point we do this small signal application, so that we can get a good amplification. Because here we are getting the maximum GM. Before that GM is increasing, and after that, due to the velocity saturation, the current is saturated, hence GM is reducing. Okay, so the minimum of the GM somewhere where current is saturated is some 4.5 micro. This is minimum is 4.5 microsiemens. Okay, so the point is that why we choose the midpoint biasing is that only we are getting the maximum GM there. Okay, before that GM is less, after that GM is less. So around this midpoint we can apply the signal, because the slope of the current is maximum there, so hence GM is maximum. Also we can see the GDS plot also. Then we can take out a few more conclusions out of it. So the point is that the output maximum can reach my VDD, near VDD. Okay, and it is reaching near ground, but it is not exactly ground, it is near ground, because few millivolts up, which is a 211.4 millivolts here. So it is not going to exactly ground. So this was the, I think, my motivation to explain in this way, so that you can understand and you can conclude a lot of things here, because these are the important questions which can be asked anytime in the interview or for any company. I'm not pointing out any particular company, but yeah, these are the very basic questions. The single or can say one stage means amplifiers, they are very important. Means common source amplifier with current source, common source amplifier with resistive load, common source amplifier with diode connected PMOS transistor, common source amplifier with means PMOS external biasing, means practical current source, means common source amplifier with other possible current with the cascode devices. So we will see these things slowly in the coming as CTQs. Most probably in the CTQ 9 I have given is all these circuits so that you can analyze in this way. Okay, so now I should recap whatever I discussed and we will then end this session. Okay, so this way we proceeded. This is an inverter. So what was the discussion? The point was to get a GM plot and ID plot, and after seeing, I think I have cleared all the things in great detail. I have explained here so you can understand. So we went through the basic concepts. We have taken some takeaways here with the discussion, and after that we entered into the subthreshold region. What is the subthreshold conduction, and how it is defining, or means how we can define the current there. So that I've written the exponential equation here. So this thing is written here, exponential relation. So this is also important in this regime, in this subthreshold regime by BJT and MOS, similar characteristics in subthreshold region of. So because this is the exponential equation which is directly like a BJT current equation, which is IC saturation current exponential VBE by eta BT. It is looking like that only. Okay, so we can see in some points I think I discussed in the previous video also. BJT is like a better current conversion, means it has the current converting capacity better than this, means it is a GM that I call GM of BJT is more than the GM of MOS for particular input. So this is the advantage of BJT. There are a few other advantages also, we will see in some other lecture. Okay. Because of the exponential dependence, we calculate the GM of the BJT from here, and for in general the operation of the MOS happens in this quadratic region, or can say this non-exponential region somewhere here. So here our dependence is on the quadratic, so we get the GM which is nothing but linear dependent on something, so we cannot get that much GM here. Okay, rest thing I explained here, what is going to be the maximum value, minimum value. Okay, so why it is not reaching exactly VDD. So practically you can see this, somewhere here I already shown the at the end, but ideally it is not like that. Okay, so I think all the things are covered now. I should end this session. Whatever you can extract from it, do it. If there is any doubt, you can post, and after that we will see what next can be done in this particular behalf. Okay, so this was my particular result window that I have taken, so you can understand that exactly what I was telling is happening here. Not output is reaching to VDD minus VTP in practical, it is reaching somewhere near to the VDD, and not exactly it is reaching to the ground, it is reaching some constant value so that it can maintain the constant current across it. So I think it is enough for this video. Thank you.